ladies and gentlemen, welcome back to another episode of the Engine Shed. Today I'm doing something quite substantial. It's something that a lot of people have asked me about in the past, and it's something I've finally got my ass in gear to getting around to do. So today's video is all going to be about helixes, and for the sake of continuity and making sure that the quality of the videos are good enough for people to follow along with my method of developing a helix, then I'm going to segment this into possibly 2, maybe 3 parts. So today this video is just solely going to be focusing on the planning of a helix or the design of a helix. Now, for those of you that don't know, I have a helix. It's been featured on the layout before, but I've never really discussed it for a good reason. It's not something that I'm particularly proud of, and I'll show you what I'm talking about. This is the helix that currently sits on my layout, and there's a lot of rubbish and stuff in there at the moment. Now, this helix has served the purpose, but it's not perfect. There's a lot of imperfections in the rises and the quality of the design, so I've decided to disassemble this helix and reassemble it with a new cantilever design, and I'll discuss that in a little bit. But this is the second iteration of the helix. There will be now a third iteration of the helix, and it's going to be a lot better in theory than this is here. So today I'm just going to walk you through how I design my helix and the best way to go about planning, preparing, and getting the calculations and the measurements right, so that you don't have to be dealing with such a headache as running a train up this thing as much as I have in the past. So follow along if you can. If you need to, pause the video. I'm going to be as plain and simple as I can be. There is a bit of math involved in this video, so don't be too overwhelmed if you can't follow along straight away. And I'll put up some documents later on at some point, but hopefully you can read my writing and I'll make it clear as possible. So the generic theory behind a helix is a grade. Okay, now OO scale trains don't tend to operate well on anything more than a 3% grade, and especially if you want to run full length trains like an 8 coach or plus steam locomotive or diesel locomotive, you've really got to be very careful about how you go about dealing with your grade selection. So for me, the distance between my top level and my bottom level is 300 millimeters. So we'll write that down. So from top to bottom, it's 300 millimeters. So that's the elevation that I need to gain in the space of the table that this camera is sitting on is 1200 wide by 1.8 meters wide. So 1200 by 1.8, 1200 by 1800. So I have to fit a helix within that space that can elevate the track 300 millimeters in clear air without exceeding a grade of 2.5%. So 2.5% is about where you want it to be. That's the maximum, that's as far as you really want to take this. So with that knowledge, we know that we have a 300 millimeter rise. We have 2.5% is our target gradient, preferably less if you can pull it off. Next, what do? Well, next thing is track and clearance. Now, we'll talk about the track first because the track affects your clearance. For a helix, I have found that flex track, especially in the climate that this layout is, tends to be a poor selection. Flex track, if it's not secured properly, can bend and warp and distort in the heat, which is not what you want for a helix. You want the helix to be very precise, very well aligned, so the track geometry needs to be on point. For that reason, I'm using Hornby set track, so the 3rd radius and the 4th radius. And I believe the codes for those are R609 and R8262. So that's the 3rd and the 4th radius. Fourth radius track. Now, the radius of these track is, this particular one is 505 millimeters to track center radius. For those of you that don't know in mathematics, R is equal to radius. And this one is, I believe, 575 millimeters to centers. Okay, so now we've established that, we And I should point out at this point, it's pretty well documented that my Helix is a double track. So of course, if you're using a single track, choose whatever fits, okay? You don't want anything much smaller than a third radius, and you really can't get anything bigger than a fourth radius. Okay, so again, it's depending on your scale, your gauge, whatever the situation may be. Evaluate your situation first before making the decision of what track you're going to use. So our next step is clearance. And we're talking about two things here. When you're designing a Helix, you've got to develop a roadbed. So we've got 575 and we've got 505. So I'm going to need at least 60 millimeters between the track centers. Okay? Which means, and for those of you that don't know, the width of the track, which you can see up here, the width from sleeper to sleeper is 30 mil and it's 16.5 mil between the track. Okay, so we got 30 and 30. So that's 15 off every side. So that gives me about 25 to 30 millimeters between the tracks, and that's perfect. That's really all you need. So with that established, we know it's 30, 30, 30. It's 90 mil. You want at least 15 millimeter clearance from the edge of the track to the edge of the baseboard. And that's 15 millimeters on either side. 30, 60, 90, and another 30, that's 120. So my roadbed is 125 millimeters. So we made the width of the roadbed 125 millimeters. Okay. From that, we know that we have essentially what will become the profile or the cutout of your roadbed. So you cut your semicircles, your quarters, your eighths, whatever it's going to be. Okay. Now I have a space to work with, and I said 300 millimeters, 2.5%. Now because this is a 575 millimeter radius track, that's the centers. We have to add another 15 and a 15. So I mean, I'm looking at, we need to add at least 25 more mil on there for there to be clearance from the edge of the track to the edge of the board. So straight away I'm looking at 600 mil, which for reference sake is the actual radius of my Helix. That's the external radius. The internal radius is 125 millimeters less. So figure out the math, people. For now, all we need to know is the 600 millimeter radius, because when you do that, you can do the circumference calculation to calculate the actual run length of your first turn, and thereby check your percentages are okay. So we know that 600 millimeters. Okay, so that's what mine is right now. Now we need to do the circumference to get the run length, or the to help us determine the grade. So we have a target grade now, and we have the known, or the target radius, planned radius. We just need to chuck it into a circumference calculation to verify that that particular grade and percentage is going to be adequate for what we need. So if the uninitiated, the circumference calculation is simply 2 pi r. Pi is a constant. Every calculator knows what pi is, and if you don't, it's 3.141599265, etc., etc. So we know the radius is 600. We know it's 2 pi r. Plug in the known. So it becomes 2 by pi by 600 millimeters, and that is equal to approximately 3770 millimeters. It's actually 3769.8 or something like that, but for the sake of this video, we're going to round it up to 3770 because that's all you need to know. Now, a grade is a percentage. So this rise over run, we want a 2.5% rise over 3770 millimeters. So it's very easy to calculate the height. In that case, it just becomes 3770 by 0.025 is equal to, I think it's about 94 millimeters. So that's a little bit too big. That's too substantial, because when you look at it, 94 millimeters, that's nearly 100 millimeters in rise. Okay, now the next thing you need to consider is how many turns you need. Now, if like me, you have a track going in this way and leaving this way, it means that you need 1, 2, 3.5 turns to comfortably be able to reach the 300 millimeter rise target that we have here, which is the case again that I've used in the past. 3.5 is what I've used for a 300 millimeter rise. So that means that we need to get, according to that, 3.5 by 94 is probably too big. So by the time we get to the half turn, we're actually going to be higher than 300 millimeters. So in this situation, that's too big. What we need to then consider is the clearance for the trains as they run up the helix. So we know that there's 3.5 turns. So height target is about 85 millimeters is what I've found to be adequate. Now to check the grade, we don't want it any bigger than 2.5%, just 85 over 3770 by 100 to get back to a percentage, and you'll find it's about 2.25%, which is good. So that's fine, that's okay. That's okay indeed, and that's in fact the grade that I have used in the past. Turns out to be okay. So from there we know that 85 millimeters is a good clearance height. So this is the height between turns. I'm just going to go onto a new page. Now when considering clearance, we know that the clearance between the roadbed is 85 millimeters. Okay, now other point, material that you use is going to be the first thing you need to consider. I use a 6mm MDF. MDF for most purposes is perfectly adequate for what you need to do. It's perfectly pliable. It's a lot easier to modify than some timbers like plywood. In terms of considerations like warping and things like that, so long as it's braced at regular intervals, you've got nothing to worry about. So from bottom to bottom, it's 85 millimeters. So immediately we lose 6 millimeters to material. So then we're down to 79 millimeters. We've got a 3 millimeter roadbed or foam track underlay. We lose another 3 millimeters. 76 millimeters is what we're down to. Height of the track is about another 3 millimeters. So you can see it very quickly adds up. And then on top of that, we have the joists holding these things in, which in this case is going to be about 8 millimeters. So 12, we've actually lost 20 millimeters off that, which gives us 65 millimeters of clear air. And it's important that you actually make sure that your locomotives can fit into there, and I can report, at the very least, most locomotives don't exceed more than 55 millimeters in height. Okay, so you're pretty safe in that respect. You've just got to be very careful, because if you're using AC electrics, of course, they've got the pantographs. I'll be doing another video on how to deal with that as well. So that checks out. You need at least 60 millimeters of clear air to fit your locomotives in there comfortably. So MDF, track foam, track. These are all approximate, but this is just generally what I've found to be accurate. This here, and I'll explain this in a bit, is the support. We're going to be using threaded rod for this, and the helix that I'm designing, as opposed to a traditional helix where it has 2 support masts going up, threaded rod, and a support joist going across, is going to be swapped out in favor of a cantilever. cantilever helix. So a cantilever helix works like this. I'm going to get some timber, affix it to a base. Now, next point I'll make is a removable base or a modular base. So this is just 9mm MDF that I had scrapped around. And to show you what I'm talking about, this here is a modular base. So if at any point I do need to pull the helix out, I can. It's not actually affixed to this table. It just makes the maintenance a whole lot easier. And in the case of me pulling the whole helix out, I can do it in one part without dismantling anything. So that's the advantage of that system. Now we've run 15 minutes. I'm going to try and make this no more than 20-25 minutes, so I've got to get a crack on. So cantilever setup is unlike a traditional setup, which would look like this. You have two threaded rods, you'd have a joist going across, and your train's running in either direction like that. Some threaded rods, some nuts, and then you just wind them up to suit. That's not what we're going for anymore, because that just causes more problems than you would ever believe. This situation is a little different. We're going to use threaded rod, bolt it down on either side of the timber, which creates a clear air cantilever, and then we're going to add another bolt on the end to affix the roadbed. The roadbed is going to sit on top of that threaded rod, and then the train can quite happily run unabated, and then that way it just allows a lot easier maintenance, and you've got a clear opening here for you to get access, which is really important. If your train derails at any point, you can get in there and actually get in there and re-rail it or remove it, whereas in the past you've got to contend with threaded rod and all sorts of things, so that's what you want to try and avoid. So the cantilever system is great, and it's worked. I've tested it, I've done a couple of little tests in this before. And from here, what do we do now? Well, from here it's important to establish that we know that we need 85mm between centers. So 85mm of clearance between the hole centers. So you get a 300mm piece of timber, you drill holes 8mm thick for a threaded rod at 85mm centers, and that will get you the clearance that we just talked about up here. The next phase is determining the relevant risers. Now this is where it gets a little bit complicated, so just try and follow along as best you can. Now earlier we determined that 3770, now we need an 85mm height. And we know that this is 3770. Now based on that, it's 2.25% of a grade. So rise over run is 2.25. In this case, we just apply a bit of trigonometry, or Pythagoras if you want. And Pythagorean theorem is a squared b squared equals c squared. You can do that if you really want. In this case, it doesn't end up being that much smaller because it's only 2.25%. So 2.25% of, or in this case, is about 3765, I think it is. 3765 millimeters. Okay. It won't really affect you too much because you know what the length of the circle needs to be. That's pre-cut. You just need to figure out what the rises are at the individual levels. So in that case, this number is important because we need to divide it into 6, or again, however many you need. So when you're doing your rises, you want at least 6. 1, 2, 3, 4, 5, 6. Start point goes around like that. end point, and so on. So I found 8 to be too many. I've had 8 in the past. It's way too many. You don't need it. 6 is more than adequate. Again, it depends on your situation. Plan before you execute anything and be patient. This stuff is really, really hard to get right the first time. So expect there to be problems. This isn't going to magically just happen by itself. Okay, now, fortunately for the rest of you, I've done a lot of the calculations already. Where did I put them? Right here. And this is where a bit of clever trickery comes in about. So, to actually execute this and determine what your actual clearances need to be, this is how I do it. So we start at 0, and this is where grid paper comes in really handy, by the way. So this is our entry, and then we move up. So for this sake, we'll say 3 grid squares is 85 mil. We go up 1, 2, 3. 85, 85, 85. Okay. Now, again, depending on your scale, I'm going to go all the way up to here, and then we're going to go 85 again. 3 grid squares. 1, 2, 3. 85, 85, 85. And then it's just a simple case of connecting the dots. So we go 1, 2, 3. And this is actually what the side profile of a Helix will look like. Okay, it's probably a little hard to tell on the camera, but that is essentially, if you were to take a profile of a Helix, that's what it looks like. So what we need to know is at regular intervals what is the height. Okay. So we've got 6 rises. I'm regretting this already because I've got to do this on the fly. I didn't do this calculation. That's okay, we'll press on. We've got to establish the height here, 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 and here, and we know that's 85. After that, everything is 85 millimeters on top of that measurement. Now we know that the last of the one is going to be right here. And I've just got to quickly do something. Right here goes 1 second. Okay, so it's 3.5. 1, 2, 3.5. That's our 3.5 turns in profile. Okay. Now, I've already done the calculations. It's very simple to do it. You divide this line by 6 to get your 6 parts. Oh, sorry guys, 1 second. Guys, we just had a postman delivering a parcel, so I had to go and take care of that. Alright, so for this scale, this length is 200 mil, so 33.3 mil is 1/6 of that. So in that case, we just go 1, and then you do it again, 66, 2, and it's 33 millimeter intervals, which this works out to be right. 3, 4. 1, 2, 3, 4, 5, and 6. Great. Now what I should point out too, just so there's no confusion, this point here, this point here is the same as this point here. And you can tell because it's level. So this cuts away back to here because you realize that it's doing a full revolution. So the height there should be the same as the height there, the height there should be the same as the height there, and the height there should be the same as the height there, which it pretty much is. So now we know how to do the height. And here's the great thing, you know, 3770 divided by, 3765, I think it is, divided by 6 is about 625 mil. So every 625 mil, again, this is not accurate. This is just an example so you guys can design your own helix. You know the run, you know the grade. It's 2.5%. So now you can do the height. So 625, 2.25% of, or 0.025 of 625 turns out to be about 10 mil. This isn't accurate. I'm just saying for the reference of the video, this is not accurate numbers. These are just off the top of my head calculations. They are probably wrong. But the plan that I've done here, which I'll explain in another video, it's correct. It's completely accurate. I've designed this in software. So we go that, 24, 38, 52, 66, and 85. And then from there, we get our measurements. Okay, so these points here are just 85 plus, because we know it's 85, 85, 85. That's consistent the whole way across. From here, and I'll just do this one to give you an example of why I'm doing it this way. So we go 10 mil, then we go 95 mil, because it's 10 plus 85. 95 plus 85, that's 180 mil. And 180 plus 85 mil. Anybody? It's 265. Okay, so now we have the dimensions that we need. And you go through and do that for all of these points. Now, why is that relevant? Because we're using a cantilever system in this situation. My timber now has the dimensions it needs for the hole centers to be accurate. So, it's an 8mm diameter hole. So, we go from hole center to hole center. So in this case, start at the midpoint, we go up 10 mil, 2 grid squares in real scale. That's a hole center. We go up 85 mil. And this isn't to scale again, but you get the idea. Hole center, hole center, hole center. Now, 300mm piece of timber. .35 by 70 pine is usually a good choice. And we know the dimensions. We just did the dimensions. So, 10 mil. 95 mil. 180 mil, 265 millimeters. Okay, why is that important? Well, these holes will be drilled out and the threaded rod will pass through them, and then you have an accurate riser to get you what you need for this. And all your MDF will just simply rest on it and will clamp in place. That's generally how I've gone about doing it, and you can execute this your own way as well. Okay, now you're going to see this come into practice in the next couple of videos, because I'm going to now go and start building the new Helix. So this is the last time you're going to see the old Helix. Please, if you do have any questions, I'm sorry if it was a bit jagged, but you get the idea. It's not supposed to be a fully comprehensive guide to how to build a Helix, because quite frankly, that's really subjective to everybody watching. Everyone's got their own method. This is what I find to work. This is how I do the calculations, and this is how I figure out what I need to make it work. Helixes are not really an exact science, is probably the point we're trying to get to here. As long as you know a few variables, you can do a bit of trigonometry and geometric calculations, you're pretty good. As long as you know the definition of grades and you know what you're working with, you know what you need. Clearance is the most important thing out of this entire thing. If you don't have the clearance for the train to actually fit under these levels, then you're not going to have a very enjoyable time running your trains. Okay, so that's all for me for the moment. The next part of the video, I'm going to be actually doing a time lapse of me constructing the barts. You'll see me drilling out those risers and attaching all that gear together. So until the next time, ladies and gentlemen, thank you very much for watching. If you do have any questions, please feel free to ask. Of course, again, I have to stress this is not a comprehensive guide. This is just me showing you how I go about doing it. If at any point it is incoherent, just ask me a question. I'm happy to answer them. And so from there, I'm just going to say goodbye and we'll see you in the next one. And stay tuned for the channel for more coming soon. Thanks, guys.